Hey, Math and Science Academy. So I had a question about this Google form. Somebody said that they just really didn't understand what was going on with it yet, and so I wanted to kind of show you some tricks for how to fill this one out, how to know what's going on here. So you'll notice that I posted some links to some videos here, and what I also did to help you out is each one of these pictures is from the part of the video where you can find the information. So I'm going to kind of talk through this with you because, I was just giving you guys videos, but I feel like I could probably teach it a little bit more too, so you really get it a couple different ways. So this first question is, which electrons move due to an electrical current? So I'm going to show you where that comes from. In this video, what you can see is it's the valence electrons, right? So most of the electrons in an atom are bound pretty closely to the nucleus. They fill up. There's 2 electrons in that first shell, 8 in the second, 8 in the next one, and then whatever ones are left over, those are the valence electrons, and those are the ones that are going to travel. Okay? Let's see. So what is a conductor? So that comes from this video. A conductor is something that conducts, that there are a certain number of valence electrons that can flow through it easily. Each one of the atoms in that material has 1 or 2 electrons that can flow free, okay? 1 or 2 valence electrons. So you'll notice if we look at the periodic table that you already have seen some of these patterns here where these have 1 valence electron, these have 2 valence electrons, but the most conductive materials are actually copper, silver, and gold, which are transition metals, which you'll learn more about in chemistry, okay? So let's look at the next one. So I just answered this one for you. How many free electrons or valence electrons does a material that is a good conductor have? It's 1 to 2. 1 to 2 valence electrons that can move. Each atom has 1 to 2, so that adds up to a lot, of course. Okay, this one references. We're talking about waves here because electricity is a wave of electrons. What we find out in these videos is that the actual electrons, 1 electron is not moving very far. This works a lot like a wave in the ocean where if you are floating in the ocean and there's waves going over, you're not going to move the whole way with the wave. You're going to move a little bit with each wave. And that's what happens here. We have tons of pulses of waves going on here. And what it does is it's the energy that's traveling through the wave. It's not, meaning what I'm trying to say here is waves carry energy. They don't necessarily move things. Sometimes they move things, but electromagnetic waves don't actually move the electrons. They just kind of push them a little tiny bit, okay? So this is showing you that idea. The people stand up and sit down. They're not actually moving, but the energy is passing through them. The wave is passing through them. That's what happens with electromagnetic waves. Okay, so then electrical wires are made of a conducting material like copper, surrounded by an insulator such as rubber or PVC. So the insulator acts as a waveguide for electrical current. So basically, what I want you to understand here is what would happen if that insulating material was not there, right? How would that electricity move? Yeah, the idea here is it's acting as a wave guide. It's carrying that electricity through the copper wire, so that insulator is kind of keeping it focused. It's keeping it traveling in that one certain path, okay? So then we're looking at series circuits versus parallel circuits. A series circuit, you can think of a series as a chain of electrons, basically. Those electrons are, and this comes from this Bozeman science video, which starts off, this is a series electrical circuit and this is a parallel circuit. So a series circuit has just one wire basically that these electrons are traveling through, and each time it has to go through what's called a resistor, or an appliance, a light bulb, whatever, that the amount of amps is lessened by half in this example. So what this does is, it's a simple way to wire something, but it means that if even one of those lights goes out, then the whole thing is dead. And also, those lights are gonna, the more things that are on that wire, the dimmer those bulbs are going to be. Okay, so that's the idea there. When you add a bulb to a parallel circuit, so this is actually how Christmas lights work. If you have one bulb and a string of Christmas lights go out, it's not going to affect the whole thing because they're wired with parallel circuits. So these are good because, I mean, they do require a lot more wiring. It's a more complex structure, but what it does is it means that each one of these, like you can have one die or break or whatever, and the rest of them are going to go fine, or going to be shining just fine. It also causes more amps to be going through the system as a whole because each one of these appliances has its own wire. Basically, like it doubles. So like instead of having, if you start off with 9 amps, you're going to end up, instead of having it, you are like halving, meaning like half. You are going to actually increase each time you add a light bulb. So that's that. That's how you do this one. Hope that helps.